Chapter 3, Measures of Centrality. Okay, first we want to look at distributions of data, and we will consider distributions a little bit more in other chapters, but in this chapter we want to look at essentially defining what distributions of data are going to include. And so a distribution of data will include information about its shape, center, and spread. And this chapter being measures of centrality, obviously we're going to focus on the measures of center. Measures of centrality include the mean and the median. First we'll consider the mean. For a sample of n equals 5 numbers, the numbers 2, 3, 4, 1, and 5 for example, we could find the total of those numbers by adding them all up to get 15, and the count or the number of values that we have is 5. So the sample mean is computed as 15 divided by 5, which gives us 3. Now this is what we would typically consider an average. The symbol that we use to represent this sample mean is called x bar, and it's the letter x with a line over top of it. We refer to that as x bar. The mean is also probably the most common measure of centrality. Now let's look at the median. The median is considered the middle of the distribution of data. There are two different ways of calculating the median. One way if we have an odd set of numbers, and a different way if we had an even set of numbers. If we have, for example, n equals 5 numbers, the numbers being 8, 5, 1, 2, and 9, the first thing we need to do is order the numbers from lowest to highest, which would yield 1, 2, 5, 8, and 9. The median is then the middle of the ordered observations, which in this case is m equals 5. Now let's consider what happens when we have an even number of observations. Consider the values here in our final scores data set where we have the students and their final scores. You can see that the final scores are not sorted from lowest to highest. And so as part of calculating the median, we need to put those final scores in order from lowest to highest. And so here we have done that. So now as we count in from the outsides, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, you can see that we have two values, 78 and 84, that are in the middle of this ordered data. And so in order to find the median, we take the mean or the average of the two middle numbers. And so finding the average of 78 and 84, we get 81, which is the median for that set of data. If we look then again at the odd number of observations, we have 1, 1, 2, 2, and 3. We only have a single value that is in the middle of that set of data, and so that's why 5 becomes the median for that set of data. It is very important that you remember to order the data from lowest to highest before finding the middle value, because if the data are in some other order, you will get some other value for the median. In fact, every time you reorder the data, you could get a different median, which is why we need to order the data first so that we know we're getting the middle of the data. Now let's look at how we might compute the mean and the median in StatCrunch. Here we have the final scores data loaded into the StatCrunch spreadsheet. StatCrunch has, under Stat, several different options for statistics. If we go under Stat and choose Summary Stats and then Column, it will give us the summary stats for a given column or set of columns. Here it asks us which column we would like to find summary statistics for. We would like to find the summary statistics for the final scores, and so we choose that column. Then we go to Next, and it allows us to choose which summary measures we would like. Now for this example, we would like to find the mean and the median, so we will unselect all the other values. Now we're just left with the mean and the median, And so we will calculate those values. And that tells us that 81 is the median, which is what we found previously, and the mean is 78.9. So that is how we can calculate the mean and the median using the computer. And it may seem like it's just as easy to do it by hand, but when you have hundreds or even thousands of values, then it can be very difficult to find the mean and the median doing so by hand. Now let's consider the differences between the median and the mean. Consider the numbers 1, 2, 3, 4, and 50. Essentially, we have two different groupings, 1, 2, 3, and 4, and then we have 50, which is far away from the rest of the numbers. If we look at the 50 as kind of an outline value, we could call it an outlier. Then the median is computed as 3. Now the median of 3 is within our group of 1, 2, 3, and 4. But if we just found the median for those 4 values, it would be 2.5. So it is reasonable that since we also have a 50 in there, that it should be shifted over to the right, and that it shouldn't be a 2.5, but it should be higher than that, and that's why it has a value of 3. The mean, however, has a value of 12, which is not close to any of the values. It's not close to the 1, 2, 3, and 4, and it's not close to the 50 either. It's just out there in the middle of nowhere. So the mean is not a very good measure of a typical value in our data. The median, though, essentially treats all the numbers, including the 50, as ordinal ranks, and it identifies the middle of the ranks, not considering the magnitude of the values. So it doesn't consider the fact that 50 is so far away from the 1, 2, and 3, and 4 that it should shift the median all the way over somewhere like 12 like the mean did. It keeps the median in where the bulk of the data are, which is why when you have outliers or very skewed distributions, the median is a better measure of center than is the mean. It's more appropriately used. If you look at the two distributions here at the bottom of the screen, you can see that the one on the left is positively skewed, meaning that the tail is in the positive or the right direction. So we've got some values that are way out here, like this 50 value that we had in this previous set of numbers. So we have several values that are way out here, but the bulk of the data are here around 10, 9, 8, and so forth. We have just the opposite with the negatively skewed distribution. We have a lot of values that are here between, say, 20 to 40, and then perhaps just a few values here around 10 and 1. And so the skew, it's called negatively skewed because it's skewed in this negative direction or in the left direction. So as you see, the values of the median and the mean for each of these two distributions, the median is always going to be where the bulk of the data are. So as a measure of centrality, essentially it's telling us where the middle of the bulk of the data are, which is right here. The mean, however, is always going to be pulled in the direction of the skew. So in this positively skewed distribution, the mean is further to the right than is the median. In the negatively skewed distribution, the mean is further to the left than is the median. The mode represents a preference, or the most common choice. The mode is typical for qualitative, meaning nominal and ordinal data. The mean and the median are typical for quantitative or interval and ratio data. And so that is why I do not consider the mode necessarily as a measure of centrality, because it's going to find the value that is most common, whether that's a central value or a value on one of the ends. It does not make sense to compute a mean or a median for nominal data. Here's an example to show that. There are 3 movie genres currently at the theater. 1 for drama, 2 for sci-fi, and 3 for horror. So we're just giving them a number, but those numbers just represent the categories. and there's no order to them, so this is a nominal variable. Of movie attendees last weekend, 300 chose drama, 100 chose sci-fi, and 100 chose horror. If we were to write out all 500 observations then, we would have 300 ones, 100 twos, and 100 threes. If then we computed the mean, the median, and the mode, the mean would be found by adding up all 300 ones, all 100 twos, and all 100 threes, and dividing that total by 500, and we would get 1.6. The median would be found as 2 because essentially we would line up all those values, all 500 numbers, and we would find which number was in the middle, and it would be a 2. The mode is essentially just going to tell us which value occurred most often. And as we had 300 ones, we know that the number 1 occurred most often. How do we interpret the mean, the median, and the mode? We would interpret the mean as the average movie attended was a cross between drama and sci-fi. That is incorrect because we're not looking at a cross or a mixture of movie genres. We're looking at the occurrence of those different genres. And so it would be wrong to say the average movie is somewhere in between drama and sci-fi, because those genres don't necessarily have to have anything in common. You can look at the interpretation of the median as the average movie attended was sci-fi, because that was the middle value. But that's wrong too. Sci-fi was not viewed any more or any less than horror movies. So why would we say sci-fi versus horror movies? The only reason it came up as the median is because that's how we ordered the values. 1 for drama, 2 for sci-fi, and 3 for horror. Because sci-fi was in the middle, that's the one that came up as the median. But we could have just as easily called horror number 2 and sci-fi number 3, and then the median would have been horror movies. So it doesn't make sense to find a median for nominal values either. But the interpretation of the mode is dramas were more frequently attended than sci-fis or horrors, which is okay because it makes sense, and that's really what we're trying to say. So it would be inappropriate to use a mean or a median for nominal data, but it is very appropriate to use a mode. Now let's look at some summation notation. Essentially, formulas can be generalized using letters and symbols. For example, x1, x2, x3 up through xn could represent n data values. No ordering is implied in those x values. x1 just means the first observation. Whether it's the lowest or the highest or somewhere in between is not implied. Then this symbolism right here represents the summation of 5 observations. So the way you read this is this capital Greek letter sigma is the summation sign. And this I equals 1 up to 5 means there are 5 observations and they are all indexed with this letter I. And so x sub I just means we have observations that are going to be indexed by the letter I. I equals 1 would mean x1 or the first observation. I equals 2 would mean x2 or the second observation, and so forth up through 5. And so what we're doing here with this summation sign then is we're summing or adding all of the observations 1 through 5. The reason we use this symbolism is so that we can write formulas that can be used for any set of data. If we don't use the symbols but use the actual numbers when writing a formula, that formula only applies to those specific numbers. I know that makes it a little bit more complicated for individuals, but we use those symbols in mathematics and statistics so that we can introduce formulas that can be used throughout the semester. So x bar, the sample mean, then becomes the summation of all of our observations from 1 to n, so our n observations, whatever that total is, divided by n, which is the number of observations or the count. So that formula right there represents the sample mean. we could have written it out as add up all the observations and divide that total by the count of the observations, but that takes up a lot more space. Using the final scores data from table 3.1, the mean can be calculated by adding the scores x sub I and dividing that total by the count n. That formula can then be represented by this formula right here using symbols. Now let's see what happens when we add or subtract, multiply, or divide a constant from each of the data values in a sample. So we start out with this sample of 5 different values: 5, 8, 6, 2, and 4. So that is what we will call our original data. What happens if we add a 3 to each of those observations? If we take the 5 and add 3 to it, we get 8. Take the 8 and add 3 to it, we get 11, and so forth. What does that do to the mean? It is the same as if we had taken that original mean of 5 and added 3 to it. So adding a constant to each value in a distribution has the effect on the mean of adding that same constant to the sample mean of the original data. What happens if we subtract a 2 from each observation in our data? That would be the same as if we had subtracted a 2 from the mean of our original data. So the mean of this set of data where we've subtracted the 2 is 3. What happens if we multiply every observation by 2? Well, we have the 5 and we multiply it by 2, we get 10. We have the 8, we multiply it by 2, we get 16, and so forth. Then the effect that it has on the mean is the same as if we had multiplied the original sample mean by 2, that constant. If we divide each observation by a constant 2, that is the same as if we had divided the original sample mean by 2 as well. So looking at this table, you should see what effect adding, subtracting, multiplying, or dividing a constant has on the mean. Now let's look at sums of deviations. A deviation is a difference. In statistics, the difference between an observation and the mean of a sample. The deviations between an observation and the mean is always less than or equal to the deviation between an observation and any other constant on average. So what we do is we have this original data set. We find the sample mean, which is 7. And then in this next column, we're subtracting that sample mean from each of our individual observations to give us the 8, 1, -1, -5, and -3. We then square each of those differences or deviations, because if we don't and we add them up, we're always going to get 0. So we square those deviations and then we add them up to get 100. If we do the same thing with the median instead of the mean, we get 105. Notice that the sum of the squared deviations from the mean is smaller than the sum of the squared deviations from the median. It can be shown that using the mean in the deviations will always lead to a smaller sum of squared deviations. Measures of central tendency or measures of centrality are used as inferential statistics. Ideally, our sample data are selected in such a way that they should be representative of the population that they come from. The sample mean, which is represented again by x with a line over it, or x bar, is an estimate of the population mean, which is represented by the Greek letter mu. The sample mean, which is a statistic, will seldom equal exactly the population mean, which is the parameter. But there is some error associated with inferring what the population mean is from the sample mean. That error is referred to as sampling error. and it is the difference between the statistic that comes from our sample and the parameter which comes from the population. In summary, the mean and median are the most common measures of centrality, with the mean being used a little bit more than the median. The mean is often used in statistical analyses, but in skewed distributions, the mean falls more towards the tail of the curve, therefore less useful than the median for skewed distributions. The mode is appropriate to use with nominal and ordinal scales. The mean and the median typically are not. And that is the end of Chapter 3, Measures of Centrality.